not bad. Alrighty, so chapter 8 review packet, just so that everybody knows the answers for the chapter 8 review packet. 1 is C as in cat, number 2 is D as in dog, number 3 is B as in boy, number 4 is C as in cat, number 5 is A as in apple, 6 is A as in apple, 7 is B as in boy. All right, 8 is D as in dog, 9 is B as in boy, 10 is C as in cat, 11 is A as in apple, 12 is B as in boy, 13 is C as in cat, 14 A as in apple, 15 B as in boy. So, as I said, during the review day on Wednesday, if you have a question on something and you can't figure out why, what's wrong and what's going on, you could ask me then. You could also ask on Thursday. But today, we get to hit these wonderful, wonderful application of vectors problems. Yeah.
So we need both this white packet and the yellow packet done by Friday?
By Friday, all 3 packets will need to be done because we're taking a final on chapters 1, 2, 3, and 8.
On Friday?
On Friday.
Oh, oh.
Yeah, 8 was blue.
I think I put that in already.
Yes, you did, and I was going to give that back to you.
Is it 50 questions? To be honest, I definitely thought that was more.
It's split up between, it's 50 questions total. It's split up between
so it's like the
first part and second part, so approximately 25 for each.
Oh, okay. I have to too.
So it's 50 points both the finals?
No, we'll just grade it all when you get it done.
Okay.
Yeah, as a 100-point final. Yeah.
Is that going to be done on Friday? Do you want me to take it on Tuesday or?
I suppose we'll have to. Get it done. Alrighty, applications of vectors. Woohoo! We've covered quite a bit of our objectives up there. There wasn't a whole lot. We have the head minus tail rule. Just hang around. Find the magnitude of vectors. Did that with a couple of them that you had unit vectors for me today. Use vector addition and scalar multiplication. And then find a unit vector. Those were the 2 that you had questions about. Homework were unit vectors. And then resolving a vector. And that was just figuring out what those component forms are. So applications of vectors now make us think, what are we finding when we do all of this, and what does it represent? So applications of vectors, the velocity of a moving object is a vector because velocity has both magnitude and direction, and that's what a vector is for. So that you can see not only how fast is it going, but in what direction. And the magnitude of velocity is speed. That's what it is. So when they talk about these vectors and they give us the speed, we should be going, yes, I don't have to find the magnitude. They're telling me what that is, and use that information. So example 7 says we have a very lovely little DC-10 jet aircraft, and it's flying on a bearing of 65 degrees. Now that's a problem. Bearing. We don't do the math with bearing. We do the problem with our math from the positive x-axis as being 0. So immediately when I see bearing, I start thinking, great, now there's more I have to do with this. But this isn't bad, because if the bearing is 65 degrees, and remember that's from due north, then we can figure out that from the x-axis, that's 25. And it doesn't take a whole lot of tough math, but it's just an extra little thing that you have to catch. And it says it's at 500 miles per hour, so I'm thinking to myself, excellent, magnitude, you just gave me that. Find the component form of the velocity of the airplane. Okay, that's just resolving the vector. Recall that the bearing is the angle that the line of travel makes with due north measured clockwise. So they were going to give us a hint to try to remind us, don't just put bearing in here into all the math that you do for these problems. So when we did these, we said, okay, if you resolve a vector, what you need is the magnitude. Well, that's 500 times the cosine of the angle of the direction, and in this case we're going to use the 25 degrees, and again we're going to have to watch that when we get to the final as well, radians versus degrees for things we're doing. And then we'd have 500 sine of 25 degrees. And then it's just a calculator, we figure out, hey, they gave us the magnitude here. That's what I need. I need those pieces. So you have to make sure you're in degrees. And I already punched them in, so go ahead and punch it in so you make sure everything's still in degrees and everything's working right. But we just needed 500 cosine of 25 and 500 sine of 25 because they just said, hey, you know what? Here's what we want. We want the component form of this vector. And that's how we get it. Magnitude times the cosine of the angle, magnitude times the sine of the angle. All right, everybody's getting the same thing? Good. So we don't have any sitting in radian mode out there. So to our 3 decimal places, we had 453.154 and 211.309. And then I always check and think to myself, does that make sense? And both of those are positive. It should be first quadrant. Well, yeah, there it is right here. I mean, this is definitely a first quadrant vector. So they should both be positive. Well, that's not a big scary word problem. No, that's not a big deal. So, of course, we gotta pump it up a little bit. Put it on steroids and see what happens. And that's what's happening in this next problem. Is we're seeing all the recorder lines are just in the wrong spot. There we go. What happens when things get a little more complicated? So, calculating the effect of wind velocity. Pilot Megan McCarty's flight plan has her leaving San Francisco International Airport and flying a Boeing 727 due east. Okay, so supposed to be flying due east. Problem. There's always wind. You know, she can start out due east, but she's probably not going to end up there unless they account for wind. So there's a 65 mile per hour wind with a bearing, there's my first problem, bearing of 60 degrees right here. And it says, find the compass heading McCarty should follow and determine what the airplane's ground speed will be, assuming that its speed with no wind is 450 miles per hour. So, the picture is showing us that this AC, that's the wind. That's our vector AC. And AB is where she's going to have to fly because the wind is pushing her. But where she wants to get to is the resultant vector right here. And I'm going to go ahead and put that little dashed line there so everybody can see. If we took the wind vector and moved it down below, there's our diagonal for our parallelogram, and that's the resultant vector. So what we're really going to have to do is add vector AC and AB so that we can figure out what that's going to give us for AD. So vector AD is going to come from adding vector AC plus AB. All right, now I love it if I can get them in component form right away and have everything all work out nice. So, first of all, we got that bearing issue. Well, if this is 60, then what measurement should we be using for vector AC for direction? Yeah. Did they tell us how fast the wind was going? Excellent, because that's magnitude. So for AC, we're going to have 65 cosine 30 degrees and 65 sine 30 degrees. I'm not punching anything in at this point because I'd like to keep everything exact. And with the trig in it right now, this is exact. All right, now I need to figure out stuff about AB. Okay. Oh, good. They gave me the magnitude. All right, so AB equals 450 cosine. Problem. I know what that angle is. Well, hopefully something will come up so we can figure it out. So I'm just going to have to put a little theta there for now. And 450 sine of 30. All right. Now I want vector AD. So for vector AD, I have to add those component forms. So that'll be 65 cosine of 30 degrees plus 450 cosine of theta, and then 65 sine of 30 degrees plus 450 sine of theta. Here's the problem. Without theta, I can't go any farther. Unless there's something in the information that they gave me that's supposed to be helpful. So I go back and I think she's supposed to travel due east. So if she's supposed to travel due east, won't that mean it has to be some number 0 for that vector? Wouldn't it have to lie on the x-axis? Well, then that means this mess right here has to come up with 0. And that means I can solve for theta and I can figure out what it is. So 65 sine, oops, I forgot the S, 65 in 30 degrees. 65 sine 30 degrees plus 450 sine theta equals 0. Has to. Well, let's go ahead and move that 65 sine of 30 over to the other side. 450 sine of theta equals negative 65 sine of 30 degrees. Divide by 450. Sine of theta equals negative 65 sine of 30 degrees over 450. Is that enough for us to figure out what theta is? How do we get it? Yes, good, you're remembering that. Good, good, good. We need the inverse sine of all of that mess. So, let me get my calculator working on this. So it was 65 sine of 30. Divided by 450. Inverse sine. That mess. Now, I think ahead about whether or not I'm going to need that again. And chances are pretty good when I have to find the airplane's ground speed that I might need that again. Do you remember how to store things? Been too long? Store is just to the left of the 1. And then you have to pick a letter that you want to put it in for. But you have to say alpha and whatever letter it is. I'm just going to hit alpha and X, which is the store button again. So that's going to keep my negative 4.141634351 so that if I need it, it's there and it's perfectly held. So that helps us out. Move it this way. By giving us our little theta of about negative 4.142 degrees. Okay, now we know what theta is. We also know what the y portion of our component form of the vector is. It has to be 0. But we don't know the x component yet. Can we find that now that we know what theta is? We sure can. So, x component 65 cosine of 30 degrees plus 450 cosine of negative 4.142 degrees. Now we can just punch this in backwards and maybe we wouldn't have needed to store it because we can go back to what we had and put cosine times 450 and then just add this piece in there. Or you could recall it and put it in that way, whatever you want to do. But in the end, cosine of that angle and we need to take that times 450 and we need to add 65 sine of 30. That's not what I got earlier. Is that what you got? Did I miss a number?
I got 505.
Yeah, that's what I got before. And I had this in degrees. Well, let me try again with my stored thing. All right, so I'm going to punch it in with my store button. 65 sine 30. Should have just gone with my store. Plus 450 cosine. That's what it was. I punched it in with sine. What happened here? There we go.
Now it's 6 times cosine.
I'll just start that over. There we go. Plus 450 cosine of my x. There. That's better. 505.117. All right. So there's our component form of the vector so far. Unfortunately, they didn't just ask us for component form. Blah, 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 and then it says, find the compass heading the part you should follow. Oh, well, we better go back and talk about that. Let's see, we got our little negative 4 point whatever, right? This option here. Which would mean it was right here. But that's not bearing. I mean, that's the good stuff for the math we needed to do, but that's not bearing. So how can we tell them how to go from due north here all the way over to here? Just take the negative off and add 90. Yeah, this is 90 degrees right here. They need to go another 4.142. That's 94.142 for bearing. Degrees. Okay, we got their bearing taken care of. Questions? Because bearing is from due north. That's the whole problem. When you do these problems about airplane travel, they're going to give us stuff in bearing, but we can't use bearing when we do the math. So we have to convert bearing and then convert it back at the end, which stinks. But at least we can tell them exactly what they want to know. All right, the other thing they wanted to know, determine the airplane's speed. Well, that's the magnitude of this lovely little vector right here that we found. So that will be, because in component form, it's always with 0, 0. That'll be the square root of 505.117 squared plus 0 squared. Wait a minute. Won't it just be 505.117? Exactly. Square root and squared. We just need to put the appropriate label on there. So what were they talking about for speed? Well, that's good enough. MPH. And with a problem like this, I mean, look at everything we have up there. We probably want to put one sentence at the end, just explaining everything. The pilot should travel at bearing 94.142 degrees at 505.117 miles per hour. Bam. All together. That's a lot to keep track of. At the beginning, it is best to just kind of stop and summarize. Okay, what do I really need? I need to add these two vectors together and get my answer. So now how do I get those two vectors and work your way through it? Of the word problems we're going to do today, that one I think is the most complicated, because you have a lot of things to keep track of. This next one is like a baby problem now. All the things we've done. It says a force of 30 pounds just keeps the box in figure 6.15 from sliding down the ramp, inclined at 20 degrees. So I look at this and I see, yep, they've got the incline here. They've already given us a nice little box for the parallelogram and shown us that this would also be 20 degrees right here. And they want the weight of the box. And the nice thing is that they labeled it for us, but it makes perfect sense. I mean, that weight has to hold it down. That's the pressure of holding it down. So what they really want to know is W. So let's see, is there something we know here? A force of 30 pounds. Oh, well, that's this force right here. That's 30. That's what's keeping it from sliding there. But wait a minute, if that's a parallelogram, doesn't that tell us what this is down here? Exactly. And this would appear to be something we could use right triangle trig for. This is opposite, and this is hypotenuse. Which trig function should we use? Sine. The sine of 20 degrees equals 30 over W. Like I said, some of these you don't want to overthink. It'd be very easy to do. So we'd multiply by W, and we would divide by the sine of 20 degrees. All right, so 30 over the sine of 20. $87.714. And then we better label it 87.714 watts. Pounds. Yep, that's the weight. So that was a lot easier than the airplane power. Basically, they gave us the picture, which is great. And I believe in the homework, because I don't remember this homework taking particularly long. It's the same kind of thing when you get the picture and everything's all laid out for you. Now this one. During one part of its migration, a salmon is swimming at 6 miles per hour. Okay, here's my salmon. Swimming at 6 miles per hour. And the current is flowing downstream at 3 miles per hour. Okay, I'm going to start putting some of these magnitudes on here. This little guy right here is 6 miles per hour. But the current is fighting the fish at 3 miles per hour at an angle of 7 degrees. Well, that messes up the math because this isn't 7 degrees. We wouldn't use 7 degrees for that. We'd think of it as here's our new origin right here, and we'd use negative 93 degrees for that. That 7 doesn't really help us out a whole lot. So now let's see, how fast is the salmon moving upstream? Well, here we go again with that's the resultant vector. The salmon is swimming like crazy, but the current is fighting it back, and it actually ends up traveling at vector CB here. So let's go ahead and set up our little CB equals CA plus A, they don't have a letter there, AB. Yep. Oh, thank you. Thank you. I kept thinking about that last problem. Okay, so negative 83 degrees because we're swinging down and there's a 7 degree gap. Alrighty, so let's figure out what's going on. Our little vector for the salmon would be pretty easy. I mean, if we think for components for a vector, we'd actually start down here with 0, 0, and that would be 0, 6 because it's going straight up. But our component for AB, well, we have everything we need right here. We've got the 3 miles per hour and the negative 83 degrees. So 3 times the cosine of negative 83 degrees. And 3, bless you, times the sine of negative 83 degrees. And I'm not going to be able to fit my own arrow over there for that. So that's what we're trying to find for CB. Well, we could go ahead and add those components together right now. That's going to be 0 plus 3 cosine of negative 83 degrees. And 6 plus 3 sine of negative 83 degrees. And with this one, they want to know how fast is the salmon moving upstream. So again, this might be one where we want to store what we're putting in there, so that we'll be able to use it exact instead of all of our rounded stuff. All right, so away we go. The x component was 0 plus 3 cosine negative 83 degrees. So 0.366. And then the other one was 6 plus. And then we have 3 sine of negative 83 degrees. 3.022, whatever. Now, like I said, we're going to be using these numbers in a little bit, so let me go through the whole store thing again, even though hopefully after you got reminded before, you're okay. 3 cosine of negative 83. How do you do store? Okay, STO. Maybe I'll just put it in A this time. I've got my capital A right above the math button, so alpha A. That's going to keep that 0.366 in perfect form for me. And then 3 sine, 6 plus 3 sine, negative 83. And I'll just store that in B. Store alpha B. Just in case we should need that later. All right, so far we have our component form of 0.366, comma, 3.022. All right, next up, it said how fast is the salmon going upstream? So what do we need to find about that? Magnitude, exactly. It's in component form. That means that the initial point was at 0, 0. So this is just going to be a little magnitude of CB. And they had it as, oh, I thought they'd given us a B for that one. They didn't. A magnitude of CB, that'll be the square root of our 0.366 squared plus 3.022 squared. But like I said, I wanted those exact. That's the reason I stored those, so I can go back and just punch this in as A's and B's. So we're going to recall, bless you, second store. I want to recall A. And I'm going to square that. Plus second store recall. And now I want alpha B squared. And then I can just take the square root of all of that. Second square root of my answer. Oops, this calculator doesn't need all those parentheses. So 3.044. Label for that. Speed. Miles per hour. Yep. 3.044 miles per hour. And they didn't ask us for the direction, so that one would be done. You know, they didn't say what. Well, I suppose part of that is because you can't tell a salmon the direction to swim. They're just going to swim however they want to swim. All right, so 43210 me application of vectors. Yeah, some of you watched the entire way through. So. All right, it's word problems. I get that, but they're not horrible. And really, the stuff that we did in class today, the problems in the homework, where there are word problems, are just like word for word, just with different numbers, you know? So they go about the same pace as these do. Take a quick peek. Make sure there weren't any with glitches. There is an airplane one, like the one that we did that was more involved. That's number 43. And 51 has current in the stream again, but that's actually a lot closer to the airplane problem than the other ones. So, see what you can do with these.